come up and be like, hey,
yeah, you can see.
多2天。
当然不要，我还没看着你做完了。
是这个吗？
不是，这根本就是打开那个直播那个。没这
个吗？那个是一会儿就录上，这个应该这个上去它就有那个
live stream。你不点这个，他现在应该是。
来，
还没开始，你开始录吧。
开始录了。对，这个
他现在好像不用你玩的时候自己在这参与其他的，要在自己。
刚才没看到。啊？对啊，你看。他几点钟是吧？
Saw you in the parking lot to the spot.
Oh, really?
No, I just saw you like in front. I saw you in the spot. Salt spot.
It sucks. I'm gonna have to do that. 好，那我把它关了。是吧？再给你试一遍。I was hoping it wouldn't be too bad. 像它这里面有，你认识的。这个为什么一个？哎，这个 private 这样子。就你哪个电脑看的？我们看一下。
We go to dismiss the other ones, don't we?
但这个没有让你归的地方，就是刚才是规划的。它出来之后就没有了。看不到。
Computer network. Yeah, and you're in computer systems too? Yeah. Those classes, so. Yeah, those yeah, exactly. So I'm almost kind of bummed about it. So I'm going to have to force myself to get up. Just so much time. Nice. But at first I was like, I'm just going to sit there waiting.
How to make what?
Do you have any classes on Tuesdays?
Oh, the stream. Oh, how to stream? We want to stream privately, but we want to.
I've got some like family classes.
Yeah, but we want it public. I think with some of YouTube. I think usually with the private public, I usually determine when you upload it. I'll try and see if I can figure it out.
Let's go. 这里刚录的时候
a stream options tab or something like that. And I think you can change it there. Oh yeah, right there.
这个是什么？
Try refreshing the page. There we go. Yes. That was great.
Hello everyone, welcome to the CS 5530 Undergrad Database System class. So my name is Feifei. I'm an associate professor in the School of Computing. My research focuses on large-scale data management systems. That includes relational database management system as well as all this NoSQL, anything related with large-scale data processing. That's essentially my research interest. That's probably why the department asked me to regularly teach this class at both undergrad and grad level. So today is the first day of the class. So we do have a bunch of things I need to go over with you. And then we will proceed to the lecture itself. So the first thing first is to go through the syllabus with you really quickly. I sent out an announcement last night once I enabled the Canvas class website. If you check at utah.edu email address, you should have received that announcement, which contains a link to the PDF copy of the syllabus. So you can review that on your own. But so first of all, my office hours is Monday, Wednesday, right after the lecture time. The lecture ends, I believe, at 1:10. I will have about 40 or 50 minutes in between to catch lunch and do other things if needed. Then hold my office hours 2 to 3. Okay, Monday, Wednesday. If you are unable to make that office hours, always send me an email and set up an appointment. Find out time that both you and myself are available to meet, or you can meet with one of 5 TAs we have for this class. So speaking of the TAs, I'm going to introduce them today. We have a huge class, 140 students in the class. This number might change a little bit. Some might drop, some I don't. But I expect we will be having about 130, 140-ish students at the end. So the department gave us actually 4 TAs, even though we have 5 of them. That's because 2 of them are half-time TAs. So combined together, they are counted as 1 TA. Okay, so I'm gonna go over them one by one. They're sitting right here in the second row. Dilin Gangyan. He took last year, got an A. Elijah Grab. Same deal. Okay. All right. These 2 guys are undergrad TAs. They are both half-time TA. Okay. Rui Dai. Xuan Li, she's over there. And lastly, Gui Nengzhe. Rui and Xuan are master students. Gui Neng is my PhD student. So we have 5 of them. So what's going to happen is each one of them will hold a 2-hour office hour from Monday to Friday. So I'm going to ask them to spread out. So every single day we have a TA office hour you can go to. The specific time and location of their TA offices haven't been finalized yet. I'm hoping we can finalize that later this week, pending the assignment of TA offices from the school computing office. Okay. But basically every day you have 2 hours of TA office hour you can go to. I do ask you to respect their TA office hour time. What does that mean? That means if their TA office hour is up and you are still waiting to see one of the, please cancel you a TA and look for the next TA the next day, because they are paid for that 2 hours, and outside that time you have to ask them whether they are available or not. Okay, so you can always send an email to them to set up an appointment outside their TA office hours when both yourself and the TAs are available to meet. TA email address. So in an effort trying to avoid their personal email address being spammed, we're going to use this one common email address for this class. It's called utahbta@gmail.com. So it's fairly easy to remember. So if you send a question to this email, all of them are checking this email regularly. So whoever get it first among them to your email. You can always send an email to me, of course. My email address is right on top, right here. Okay. Course description. So quickly go over an overview of the class. So what this class is about is to cover relational database systems in details. You expect to learn the application side of RDBMS. That includes SQL, the data modeling, functional dependency normalization, some basics about how data are organized within a database systems, decent files, indexing, hashing, buffer. At the end of the day, basically, I expect you to become an expert in building a database application. Okay, meaning you are comfortable of writing code and interacting with the database systems. If anyone desktop or mobile or web application with the database backend. Okay, so that's the focus, okay, of this class. What will not be covered in this class is the kernel of the database management system. Meaning, if somebody asks you to build a database system itself, right? If Oracle asks you to build the next generation Oracle database server, that's not something we're going to cover in class. That will be covered in the grad level database class. In fact, in the grad level database class, we ask students to write a database kernel from scratch. So here, in contrast, for the most part, you're going to view the database kernel as a black box. We will dive into that kernel a little bit, but not too much. So the objective is really for you to understand, if you were going to build the kernel as a black box, how you interact with that, how you build scalable, efficient application on top of it. We will cover some aspects of this kernel, of this black box. So it's not entirely a black box to you, but we will cover some aspect of it, but not the full detail of that kernel of black box. Okay? Yes, question?
Just to clarify, what you're basically saying is we will figure out how to use a database, including putting out properly along with applications and everything, but we won't be writing the database itself in a way, like we're not actually writing the code that could work with all of the commands and everything.
Partially true, because towards the end, your statement steers to the other direction a little bit, right? So what you said earlier in the first part of your question is all true, right? So we're going to focus on building application running on top of that database kernel. Toward the end, you also mentioned that you're going to write code to interact with that database kernel. Yes, that's still true. What we're covering in this class is writing code to build a kernel itself. That makes sense? Right. But that being said, as I mentioned, we will still cover some aspect of it, but just not the full detail of it.
Okay.
If you want to understand the full detail of that kernel black box, you should take this class first, then go to the grad level database class in fall. Okay. For the most part, we're gonna be focusing on relational database management system. To some of you, you may not know what a relational database system is, which I will briefly discuss today. But that's basically the most popular database management system out there. Examples include Oracle, MySQL, PostgreSQL, Microsoft SQL Server, IBM DB2. All of these guys are relational database management systems. But beyond relational database management system, once we understand how to use a relational database management system and the principle behind that, depending on the progress we can make, towards the second part of the semester, we will be branching out to other type of database management systems, such as NoSQL, MongoDB for document store, and I will try to briefly discuss graph database if we have time. So NoSQL including both analytical platforms such as MapReduce Spark and from the data storage, data processing aspect, key value stores, Cassandra, HBase, things like that. I will briefly discuss those guys towards the second half of the semester once we have enough understanding on the relational side. Okay, so that's what this class is about. We'll skip the objective, prerequisite. These are not really hardcore prerequisites I will enforce, but I strongly encourage you to have these backgrounds before taking this class. So I do expect you to have algorithm data structure class taken at the undergrad level before this class, and I do expect you to have object-oriented programming experience, in particular in Java. If you don't have programming experience in Java, but you have experience in another object-oriented programming language like C++, you can still take this class. I will give a brief overview of Java, and you should be able to latch onto it and be able to carry out the project, which will be in Java, by the way. Okay. The textbook, I bring a copy of the textbook. This is also known as a cow book because there are a couple of cows on the cover page. So it's famously known as the cow book. It's written by two professors at Wisconsin at the time this book was written. Since then, one moved to Cornell, one moved to Yahoo Lab, and then after that, both of them now are at Microsoft. This is one of the most widely used textbooks, along with the other book is from Stanford. So both books are very good, but I found this book has a better description on the application side of database systems, so we're going to use this as our textbook. Okay. This book is fairly expensive. You're going to get the third edition, by the way. So it's fairly expensive to get this textbook. So I highly recommend you buy a used one, or the next sentence will be offline. You can consider buying an international edition if somehow you can get it. Or you can try to get a copy of this book from, buy a used one from the peers student from last year who have taken this class. I have a question over there. Go ahead.
I was just going to ask if we could use the international one. I was going to ask if we could use the international one.
You can, of course. It's the same content, but I have to warn you, legally speaking, international editions are not allowed to be sold in the United States, right, for various reasons. That's why I said what I said earlier was off the record, okay? Speaking of off the record, we do have, you might have noticed this, we do have live streaming, so technically it is not off the record. Okay, technically it is not, but at least I pre-code that with my my excuse. I excuse myself, right, from the sentence I said, right? But you notice this. What the camera is doing is it does live streaming of the lectures, so that if in some days you cannot come to the lecture, you can view this from YouTube. We have a YouTube channel that is doing the live streaming of the class. So in some days, if you are unable to make to the lecture time, you can watch the streaming channel on YouTube. Or you can replay the lecture video after the lecture. We're going to upload a copy of the lecture video after every lecture. Okay? So this is in place to facilitate you to review or to catch up on lecture in case you cannot make to the lecture. It is not in place to substitute physical lecture attending time at all. Right? So meaning even we have a great facility like this available, great infrastructure available like this, I'm not asking you to not come into the lecture. Right? It's not an invitation to say, okay, I have this infrastructure here, I don't have to come to lecture anymore. That's not the case. Okay? So we still ask you to come to lecture if you can. Collaboration, academic honesty, you guys are most likely being a CS student for a little while, so you know the drill, so I'm going to skip this part. Homework discussion is allowed. You can discuss with your friends on the general direction on how to solve a homework problem, but copying from another person's solution is strictly disallowed. Of course, for coding assignments, we do have, I will talk about the coding assignment more later on. Students with disability, if you have special requests to ask for certain type of accommodations, feel free to reach me via email after the class. We will be willing to accommodate whatever requests you may have. Okay. Important dates, midterm exam. So maybe I should go over the grade distribution first, and I'll come back with the important dates. So here is a breakdown of what this class will be graded on. So everything is transparent. I do no curving. So what you get is what you get. Okay, square and simple. So here is a table and a list. Basically, you can look for this when you try to figure out where you are in this class. The written assignment, we have about 5 written assignments. Together they count about 10% of your grade. Programming assignment is 30%. This time we're gonna do this in pair of 2. Okay, so you're gonna form a team of 2 and carry out the project with your teammate together. Okay. Midterm is 30% and final is 30%. Okay. Any question regarding this grade distribution? Yeah.
Do you drop anything at all?
What do you mean drop anything at all?
Assignments, interns day out, or anything like that?
No, I do not expect to drop anything. Okay. All right. We may add to, I mean, for example, homework assignment I said 5. Maybe we will do 6 each, depending on the schedule, but most likely we will just do 5. Okay. In addition to homework, programming assignments, midterm and final, we will also have some quiz. These are not graded. The purpose of the quiz is to give you a chance to review yourself and to test yourself. Each quiz comes with solution attached to its back. So you're gonna do it on your own, then check against the solution yourself. So basically, the idea is to break out into smaller chunks as we progress into the semester. And for each small chunk, I will give you a kind of quiz to so that you can test yourself, see where you stand. Okay? Any question on this? And your final letter grade is assigned strictly based on this table. And we do running, as I explained in the paragraph below. If you get, for example, 79.5 to 79.9, that's counted as 80 points. If you get 79.1 to 79.4, that's counted as 79. Okay? So I know sometimes you feel a little bit rough, especially when you are on the edge of B plus to A minus or A minus to A. It's just 1 point off, but 1 point off is 1 point off, right? So do not try to write me an email say, oh, I'm just 1 point off, can I get A? Or can I get A minus? Well, you will expect a response from me by referring back to this table and this paragraph. Okay. All right. Any question on the grading of your effort in this class. In Canvas, I have set up your assignments already. So if you log into Canvas, you look at the grid of this class, you will see a list with all this spelled out, right? 5 assignments, project plus midterm and final, and they've been properly weighted as well, meaning 30%, 30%, and so on and so forth. So as course progresses, if you just look at your last column, you can kind of figure out where you are with regard to this letter grade table. Okay? All right. So next, I'm going to talk about the important dates. So for the midterm test, we're going to do it the Wednesday before the spring break, which is, I believe, March the 9th or 10th. The Wednesday before the spring break. Okay. So the way I do this is because so that I can have time in spring break to grade the midterm test. The written assignments will be graded by the TAs as well as the programming assignment. The midterm and finals are graded by myself. I do not use TA to do any grading for the midterm and final. To make sure I can grade each submission fairly on the same basis. Because midterm and final are a major portion of your grade, so I want to make sure we are consistent in grading submission A versus submission B. So midterm and final are graded all by myself, which means it's going to take a while because we have 140 submissions for the midterm and finals. That's why I allocate the midterm slot right before spring break so that I can use spring break to do the grading. Okay. Final, I do not decide the date for the final test. The university does, and for class, meets on Monday, Wednesday starts between 11:50 and 1:30 each. The final exam time is Wednesday, May 3rd, 10:30 to 12:30. The midterm will be using the lecture time. Okay, the midterm will be using the lecture time. That Wednesday lecture right before spring break. Other important days like when to job and withdraw from the class, I provided the dates here, but please double check with the registrar if you are thinking about doing any of this. Make sure you don't miss the deadline for those. What else? The project. So the project will be building a database application from scratch. You will start from data gathering and user requirement analysis phase. Then the second phase will be, that's basically phase number 1, data modeling, user requirement analysis, design. That's essentially your phase number 1. What we will ask you to do is basically build a mini version of something like Amazon.com, right? Not necessarily a e-business website, but could be Amazon.com, could be TripAdvisor, could be something else, right? An application of that kind, as you can imagine, right? So we will do this in 3 phases. Phase number 1 is the design phase. You will do data modeling, user requirement analysis, and submit a design document at the end of phase 1. Then phase number 2 will be building a desktop application for whatever we ask you to do. Okay. So imagine you are going to a hotel. When you're checking, they always have a checking system running on that computer with a database backend. That's kind of the type of thing we ask you to do in phase 2 with a simple GUI interface, right? Phase number 3 will be moving whatever you have built on phase number 2 to a web-based environment. In particular, we're going to use Java plus JavaScript and Java plus JSP, potentially with JavaScript if you want to make your website look fancy and all that, and with Tomcat as the web server. The grading of your project is strictly based on its functionality rather than its presentation. Does that make sense? So if you want to go extra mile to make your website looks all your desktop application, the GUI interface, you want to make them sleek, fancy, nice looking, go ahead and do that, but you are not going to receive actual credit for it. Okay? It's strictly based on the functionality of your submission. I have a question over there.
So on the first GUI, are you
Can you speak a little bit louder?
So on the first one part, can we do a web GUI or does it have to be like?
You mean for phase 1?
Yeah.
For phase 1, the design does not involve the design of your interface. The design involves the logic and data modeling, the backend of the database. Okay? It does not involve the design of the GUI in phase 1.
So in phase 2, when you said the GUI, can we do that on a web interface?
No, phase 2 has to be a desktop application. Otherwise, there will be no difference between phase 2 and phase 3. Okay? Yeah?
Was that the pair programming portion of the assignment? You said you were going to be in pairs.
Well, pair programming will be carried out start from the phase 1. So even in phase 1, you're going to discuss with your teammate to carry out the design and all that, and analysis. Okay, so it will be throughout, rather than just for the programming portion of it. Any other questions? If not, I think I'm ready to jump to the lecture today. So the rule is very simple. Pay attention. You can do those things as long as you don't disturb me or people surrounding you. You watch YouTube, you do whatever, I don't really care. As long as you don't disturb me or others surrounding you. If you have questions, feel free to interrupt me anytime. Just raise your hand. I encourage students asking questions anytime. Okay? There are no stupid questions, so don't be shy. As long as you don't know or you're not sure, you want to clarify, just go ahead and ask me questions. Okay? Is that clear? All right. So, if you haven't accessed the Canvas website, you can log into the CIS and go to the class. I already made one announcement. Do pay attention to all the announcements I will make, because they do contain important information about the class. And if you go to the files section, you can download a copy of the syllabus. There is a folder for the PPT version of all the lectures that you can download and review on your own. Okay. In addition to Canvas, we use Canvas because Canvas is a private website, right? So we use Canvas to distribute quote-unquote confidential information like discussions. So there's a forum for you to enable a discussion right here. So I highly encourage you to utilize this feature to post any question you have, or to share any observation or comments you have, so that your fellow students can benefit from your observations and your lessons, right? So this is a place to do it. In addition to the Canvas website, we have a public website, which is right here. You don't have to copy this link because it's contained in the announcement I made last night. It has, what I will do here is to release the PDF version of the lecture slides. I will post homework and project description here. To make it easier for you, I will post homework and project description both here and on the Canvas website. Okay, so you don't really have to come here if you don't want to. Okay, but I just like to maintain a public website so that it's very easy for people to Google and access it without logging to Canvas all the time. Especially now they have this two-form authentication, right? So, all right. So let's go with the day 1 lecture here. Oh, by the way, the YouTube channel is right here. I will provide a link at the public website right here. So there's a live streaming link and a YouTube channel link. A YouTube channel link is a channel for this class that will contain all the lecture videos, which we will upload after each lecture. But this is what it looks like. It has not only lecture videos from this class, but other data-related courses offered by the school computing, such as machine learning, data mining, and so on and so forth. Okay. All right. Okay, so let's get started with our first lecture called Entity Relationship Model. So database systems, why we want to study database systems? Because database is the fundamental infrastructure for many applications in the field of computer science. The word database, if you think about it, contains basically two words, data and base, right? Just as Air Force Base. You know database is a place to hold a lot of data, right? Just like an Air Force base is to hold a lot of fighter jets, right? So in the same spirit, that's how the word database come from. Most applications, if not all, are built based on some sort of data, right? Even, for example, if you talk about computer vision application, an image is nothing else but a collection of bits, right? So I can safely argue that almost all applications people nowadays enjoy from the development of computer science field relies on some sort of data processing and data storage as a backend, right? With that being said, you can understand the importance of having a scalable and effective and efficient systems is very diverse, right? It's a very diverse landscape at the moment. There are many different data management systems out there, such as Hadoop, Spark, Hive, HBase, Redis, MongoDB, Oracle, MySQL, PostgreSQL, MapSQL, SQL Server, Neo4j. I list some of those most popular ones, but the list can continue on, right? Depending on what type of applications you want to build. Hopefully by the end of this class, by the end of the spring semester, you have a fairly good understanding of relational database systems. Among these guys, Oracle, MySQL, PostgreSQL, and SQL Server are relational database systems. Okay, these are relational database systems. And hopefully by the end of the semester, you can at least make a good decision on which database to use given your application needs. Okay, so that you can make an informed decision given this diverse and large landscape that you have multiple choices from. Okay, so here is an architecture overview of a database management system. To compare database management system against file management system, which you are using on databases because that's what your operating system relies on, I make a side-by-side comparison of the two, file management system and database management system. DBMS stands for database management system. Okay, so both have a user on top and has an application program. For example, if you go to Amazon.com, the backend is a database system, but you don't interact with that database system directly unless you are a system admin. You interact with that database system with an application front end, which is the website, Amazon.com. Okay, so that's essentially what I mean by that application program. It could be a website, could be a desktop application, or could be a mobile app, for example, right? So that's essentially what the application program refers to. Then the application program will interact with that backend database on your behalf through this particular language called SQL, which we will discuss in details maybe about 2 weeks from now. SQL stands for Structured Query Language. Structured Query Language. Why it is called Structured Query Language? That's because relational database management system deals with what we call structured data. It's a lot of terminology I'm going to be introducing today. If you don't understand all of them, don't worry. We will be clarifying them in details in the coming lectures. Okay. For now, just remember, relational database management system is to deal with structured data, and the language that you interact with that database system is called structured query language, in short, SQL. Okay. On the file system side, you interface through some high-level language, for example, C, Python, C++, and so on and so forth. Then those programs written in those high-level languages will be executed by the underlying operating system. Then the underlying operating system will interact with the file system to retrieve and process the data stored in the underlying file system. That's what happened on your computer, right? If you have a file system, okay? On the other side, for the database management system, you interact through, with your data through the database management system itself, using this particular language called SQL. And then the database management system will interact with the operating system. And then operating system will talk to the underlying database, which is stored on your disk, on your storage. So if you compare the two, really the difference, if you think about it, really the difference is the database management system is an abstraction of many common and popular data management tasks into this software piece called database management system, so that you don't have to always write a program in some high-level language to interact with your data. That makes sense? Rather, this abstraction gives you a nice and easy way to interact with the data stored in database systems. So that's kind of a high-level overview between the difference of interacting and processing your data through the bare-bone file system versus the database management system approach. It's just an nice abstraction of many common and useful data management tasks abstract into the system called database management system, which runs on top operating system for you. So if we take this box, so this is the black box I talked about earlier today, right? That's the black box. If you break up that black box, what is inside? So for example, if you go to a dealership, you buy a new car, you drive around, this car is really nice, fancy, you love the car. But if you're curious, right, what's inside the hood? Right, you want to open up, right? If you open up, what happens? This is what's inside that database management system. It's kind of like you open the hood of your car, what's inside that hood. So you have an application interface, SQL interface, that take user input through this SQL language. Obviously, you're going to have something called query evaluator. So what that does is it takes a user query input in SQL and translate that into something the database management system can actually understand. So that involves parsing and generate what we call a query plan, then execute the query plan against the underlying database systems. Okay. And then there are many different data access methods. We will actually be discussing some of this later in this class, even though I'm not going to cover this whole landscape within this black box, but I am planning to cover the data access part of this black box. So this refers to buffer manager, security manager, like who can access what data, a file and index manager. And then finally, at the bottom, it's your database itself, meaning where data, the physical data are actually stored. The physical bits are actually stored. They typically are organized into data files, index files, and some metadata files. We will be discussing some of this as well later in this class. What we will not be discussing in this class is that top layer, the query evaluator part, which is how the system actually takes SQL input and convert that into a query plan and do optimizations and translate that into something that the database system can actually understand. That part we will ignore in this class, and we will be discussing that in the grad level data class if you're interested. Okay. So coming back, so this is kind of like a, dive into that black box a little bit, right? Now let's come back to 10,000 feet and look at this again as a black box. So the first thing first, if you want to build a database application, is to figure out how you're actually going to organize your data into a database. And this process of figuring out what type of data to store into database and how to organize them into meaningful structures is what we call data modeling. And which is the topic of our next discussion. So there are many reasons why we want to use DBMS. I decided to skip this list because without going over the details of DBMS, it's kind of hard for you to comprehend what I mean here. So later on, once we cover enough details, I will come back and so that you can appreciate a lot of these benefits offered by a database management system. Okay. So speaking of data models, I'll give you a really simple, naive example of what I mean by data modeling. Each of you is a student, right? So suppose I want to store data or information about each of you in a database. The first thing is I need to model you guys into something that's structured, which is described by this picture right here. So each of you is a student right there. First of all, you need to ask yourself, okay, for my application, what type of attributes or what type of values I care about this group of students. So of course, each of you is different, right? You have many different attributes, But for my application, maybe I only care about a subset of common attributes shared by all of you. For example, I care about what your student ID, your first name, your last name, your login ID, your age, and your GPA. I don't care about your hobby, your home address, some other attribute that's specific to you. I probably don't care. So this process of figuring out the type of attributes that your application care about and you're gonna store in a database system, this process is called the data modeling process. Okay? And you basically need to do two things. One is you need to figure out what attributes are common to the objects you're dealing with. The object here being university student. You need to figure out what are the common attributes you care about the object, university student. And for each attribute, you need to figure out what type you want to use for that attribute. For example, if you talk about student ID, should that be a string or should that be an integer? If you talk about GPA value, should that be an integer or should that be a floating point value? So these are what we call the types of your attributes. Okay, yeah, go ahead.
Just a quick question that
Yeah.
you mentioned common. Is it common or is it a practice in database management and such that in case if you know that not everyone may have like for lack of a term, having a notes equivalency, kind of like extra information on someone that may be different for each person, but you know in general that they'll have it, like just notes in general?
Okay, that's a good question. Let me repeat the question in case you didn't catch that. So the question was, okay, we understand the process we have just described, which is to figure out the common attributes for this particular object. For example, in our discussion, university student. But what about those individual object-specific attributes? How do we capture that? Is there a way we can morph this design so that we can accommodate those? For example, for Feifei, I care about his home address for whatever reason. But for another person, I do not care. I do not care about that value. So I'm not going to have an address attribute going to my design, because once you do that, you are enforcing that value for all the attributes, for all the objects going to your database. But you might only want to do that for a small subset of it, but not for all the objects. That's essentially the question. Do you follow me? Okay. So the response to that is actually a fairly complicated question to respond to, because depending on what you're trying to do here, if you're talking about structured data and relational database management system, the traditional view of relational database management system and structured data, this goes back to the terminology I introduced earlier, structured data. What do I mean by structured data? Well, actually, you can see from this example and his question, structured data refers to the case where you have a common schema. This, by the way, is called a schema. Structured data refers to where you can use a common schema to describe all individual records of the same object type. All individual records of the same object type. So what is the object type here? Student. That's the object type. What are the individual records? Well, each of you, each student record, that's the individual record. When you can use the same structure, or in other words, a common schema to describe all records of the same object type, that's what we call structured data. When you want to use different structures for different records of the same object, that's no longer in the domain of structured data. And for that, we have, depending on how quote-unquote unstructured you want to be, you can go all the way to totally unstructured data, meaning each record is totally different from the other record, structure-wise. A simple example would be, if I want to describe each of you as a student collection, but I don't want to enforce any specific structure for each student record, what should I do? Well, I can go with a simple key value setup, a key value setup. Where the key is simply a student ID, The value can be anything. So student A's value can be totally different from student B's value. Does that make sense? So that's a totally unstructured approach. Or I can go with a semi-structured approach, meaning, for example, I ask each student to have these attributes, but some other student may have some additional attributes, like address, but not the other students. Meaning, they are not following the same structure, but for the most part, they are at least structured similarly. So that's what we call semi-structure. An example of that is, for example, you can use JSON for that purposes, right? JSON is for the most part structured, but each JSON record can have slightly different structure within it. Question? What was that called? So you go from structured data, which is what we are talking about here. You go all the way to unstructured data, which is essentially, for example, key value stored, or you go semi-structured or semi-structured. Okay. So I hope I have responded to your question. Okay.
That does make sense. I just want a clarification on semi-structure. So basically, going off of that example, for it to be semi-structure, all records have to have those base. Like, I can't have one record that doesn't have GPA.
Well, it depends, right? So if you use JSON, it's very flexible. It really depends on your setup and your requirement. You can set up, for example, in MongoDB, if you have a student collection, you can set up in a way such that you require every record has these attributes, and some record may have additional ones. Or you can set up in a way that you need to have, for example, only the key, which is student ID. The other ones are all optional. It really depends on how you set up your collection. Okay? And also depends on the database, particular database management system you're using.
Okay.
Okay? But having answered that, let me finish, then I will come back to your question. Having answered that, actually that's a great question because I can now tell you guys for the most part of the first part of our, actually 100%, for the first part of this semester, we're going to focus on structured data. Okay? Towards the end of the class, meaning in the second part of the class, we will consider talking, branching out to unstructured and semi-structured data, depending on how much time we have in our schedule. I have a question somewhere. Okay.
Yeah. So, what if you wanted like the age to be, it had to be greater than a certain value, like 10 or something? Can you set that up in just a basic key value pair structure, or?
Very good question. So what your thing is, let me repeat the question. What if I want to enforce the age value has to be at least 10? For example, we do not admit student younger than 10 years old to University of Utah as a university student. This is something called the constraint of your database. Constraint of your database, okay? And different database management systems have different ways of enforcing such constraints. Typically, we can broadly speaking, we can classify them into two categories of different approaches. One is you enforce this in the application level, meaning in your PHP, in your Java, in your C++, in your Python, in your mobile code. When user enters such a value, you say this is invalid. Does that make sense? Okay, this is application level enforcement. The other way of doing this is to enforce this within the database system itself. While setting up your database, maybe there's a way for me to specify that age value cannot be less than 10. You may wonder why you need the second approach when you have the first solution already. Well, for various reasons, right? For example, for security reasons, maybe somebody can bypass your application level code and try to insert a record that violates the rules of your database. If you do not have that second mechanism of enforcing that constraint at the database kernel level. Does that make sense? So for really mission critical constraints, you might want to enforce that at both the application level and in your database. So that if somebody wants to mess up with the data, he or she needs to really hack into both levels, which is fairly hard to do, right? So that's one reason. Now, to respond to his question further, how do we enforce such constraint? That's a question I will defer to later slides. Okay, I don't want to get into too much today on that, but we will be discussing that later on. Okay. So this is a very simple example, right? What if we complicate this a little bit more? We don't just have students, right? If you're talking about a university application, you have students, you also have classes. You also have, not only you have student and classes, you also have interaction between student and class. So to give you an example, I have students on the right hand side and another table called enrolled on the left hand side. What's missing from the picture here is yet another table called classes or courses, right? Available in the university. The enrolled table, if you think about it, is to capture the interaction between students and courses. Who has taken what classes? There's a subtle difference though between the enrolled table and the student table or the courses table. What is that subtle difference? Well, if you think about students and courses table, each record in those two tables represent a real-world physical object. Right? A student record represents a student object. That's a physical object in the real world. Imagine you have a course or class table. Each record there represents a physical object, right? Which is a class, a course offered by that university. But the enrolled table is different. It doesn't really capture something that's a physical object. It captures the interaction between one or more physical objects. Does that make sense? So an enrolled record actually captures an interaction between a student object and a class object. But itself is not a physical object. It's really just an interaction between those two objects. Does that make sense? So that's the subtle difference between the two. And how do we capture this? How do we capture this in our design process? That's something I'm going to discuss next. But before I go into that, given the things I have discussed, I have said, there must be a way to link this interaction back to the physical object that initiates such interaction relationship, right? So imagine there is an arrow here, kind of like a pointer, points back to the student table from the enrolled table. Right? Given an enrolled record, you need to somehow figure out which student this record is referring to, right? So the way we do that is to use this attribute called student ID. Okay? Student ID, obviously this is something that's kind of special. And this is something called the key of your table, right? It serves the purpose to uniquely identify a record or a physical object. To uniquely identify a physical object or record. In order for you to do this kind of inference, right? So it has to be unique because otherwise, if the student value is not unique from the student table, meaning two students can have the same student ID values, then you're going to have trouble, right? Given an enrolled record, you don't really know which student it refers back to. Okay? So that's a kind of very simple observation you can make from this example here. Yes?
So just to clarify, the enrolled table, since that's not like actual data, like that's not representing a real world object, that doesn't require, in a sense, specific unique keys in order to get the value of it, because it's not really storing data, it's just more parsing data or relating data to itself.
Well, not quite, right? The reason is the following. It's fairly easy for you to understand that we must have a key for students table because each record refers to a unique physical object. So you have to have a way to identify that, right? The same actually is true for the enrolled table as well. The reason is you have to somehow uniquely identify a specific interaction between a student and a course object.
So are you
cannot, let me finish, then you can comment on it. You cannot allow the system to somehow duplicate one interaction with another. For example, student A take class C. That has to be unique. Right? You have to have a way to tell that's different from student B take class C. That make sense?
Right.
So what is that unique key for us to identify such interaction? Well, using this particular example, there are multiple ways you can do this, right? One way to do this is you see the combination of student ID and its course ID are unique. Okay? Does that make sense? So that seems like a good solution to the problem we have, but you have to be a little bit careful here. If I tell you the combination of student ID and course ID are unique, what does that really mean? Well, this is a really tough university you might not want to get into. Why? Because if that's unique, that means the same student can only take the same class once. Because that's unique. That combination is unique. Which means this university doesn't allow you to fail and retake. Yeah? Does that make sense? Do you follow my discussion? How do we distinguish that from a university like University of Utah? I do know for a fact that you can retake my class if you want to. Of course, I don't want to see any of you next semester. But if you would like to, I'm happy to have some acquaintance. Always to have friends back. So let me finish and then I'll answer your question. So, but if that's the case, this design does not work. You follow me? How can you potentially fix that? Well, you need to add another attribute. Yeah, go ahead.
I was just going to say, could you fix it by having another column for the semester?
Yes. Excellent. By the way, that's the right thing to do, right? Whenever you feel you know the answer to a question I'm asking, go ahead and answer that. Yes. The one way to fix that is to add another column called the semester, so that the combination of student ID, course ID, and semester are unique. Now this makes sense because the same student obviously cannot take the same course for the same semester twice. If a university allows you to do that, again, that's a university you want to avoid going to because that's a scam. They're going to charge twice tuition or 3 times tuition for the same class you're taking. Does that make sense? Now I'm ready to take your question at the back.
What does it mean to have dependencies? Because it seems like that each student has a dependency on the classes they've taken to have a grade, but the arrow only goes one way. Does that mean? I'm just kind of confused about how it's working independently.
Yeah. So you're asking something called foreign key integrity constraint. It's one type of constraint I talked about earlier. One example constraint, which is H value must be greater than 10. These errors actually imply another type of constraint called foreign key referential integrity constraints, or in your language, what you call dependencies. We will come back to that later on once we have more discussion on the modeling part. And then I will answer that question. Okay. So from this simple example, you see there are many tricky things you have to figure out, right? Like from a simple enroll table, you already have many different design choices you have to make. So specifically speaking, for data modeling, you really need to go through this process, right? You want to go with the requirement analysis, like what user really needs. For example, does your university require a student take the same course only once, or you do allow them to take the same course multiple times? That's something you, as database designer, cannot make decision for. You really have to ask whoever paying you the check to figure out what they want. And you basically enforce the database according to what they want. This process is called user requirement analysis. Okay. And then you have conceptual design. That's something we're going to discuss next using ER modeling. Then you have logical design, convert ER model to this. This is what we call relational model. And then we have schema refinement and so on and so forth. So a lot of efforts in the first part of this course will be devoted into these procedures. Okay. So now let's focus with this particular bullet over here called conceptual design. So ER model is actually strictly simple, very simple. Why? Because it only have 2 concepts. One is called entities, the other is called relationships. Okay, so what are the entities and what are the relationships? So entities in a high level, refer to real-world physical objects like students, courses, departments, cars. These are entities. Okay, these are entities. What are relationships? Well, relationships refer to the interaction between entities. Okay, relationship refer to interaction between entities. For example, students take classes. Person buys a particular car. These are relationships. Okay, so it's very easy to distinguish them. Okay, once you figure out what are the entities, what are the relationships for your design, you need to figure out what information you want to store for your entities and for your relationships. What do I mean by that? Well, once you figure out, oh, I'm going to have a student entity, you need to figure out what attributes you will have for each student. Student ID, first name, last name, do I need to store their address as well? Those are the type of questions you ask right here in this step. Then, once you have the basic design in place, you ask what type of integrity constraints or business rules you want to enforce, such as the question I got earlier, age must be greater than 10. Okay? And then you want to represent your design in a very concise and succinct manner such that others can easily understand what you mean. Okay, this is extremely important, right? You can have a super smart design, but if you are unable to tell to others, unable to explain to others, it's as like no design at all. Okay? So you have to have a way to convey your design to others so that others can easily understand. And this particular tool or this particular format we're going to use to represent your design is called ER diagrams. It's called ER diagrams. Why it's called ER diagram? Because they are represented as a picture. That's why it's called ER diagrams. So we start with entity, okay? We start with the concept of a single entity. A single entity represents a single physical object. So for example, you are a student entity. You are a student physical object. Okay? So that's a single object. That's what we call entity. From entity, we go to what we call entity set. So what's the concept of entity set? Well, first of all, you need to understand what's a set, right? Mathematically speaking, a set is a collection of the same type of elements. That's a set, right? That's a set. So entity set, by the name, implies a collection of same type of entities. Must be same type. For example, this is a set of integers, right? But what is this? It doesn't make sense, right? 3 elephants. Well, I have to be a little bit careful. Maybe it makes sense, right? You define a set of everything, then it is still a set. But in the most common scenarios, this is not a set because you have different types of elements. So entity set must be a set. By that definition, it refers to a collection of same type of entities. For example, each of you is a student entity, and when I group all of you into a set, that's a student entity set. Okay? And a student entity set, all entities in an entity set, by the earlier discussion, because we're talking about structured data, again, by the fact that we're talking about structured data, what that means? Well, all entities in an entity set must have the same structure. They can have different values, but they must have same structure. Meaning, for example, if your first entity, student entity, has student ID, first name, last name, and age, all student entities in the same entity set must have these 4 attributes, no more, no less. They can, of course, have different values on these attributes, but structure-wise, they must be the same. Does that make sense? Okay. Furthermore, per the example earlier I mentioned, going back to that student table, you must have a special attribute whose values are distinct for you to uniquely identify a single entity from an entity set, or a single record from the student table, right? So that particular attribute is called the key of that entity set. For example, the key for the student entity set will be the student ID attribute, because that's the attribute that no two students can have the same value on. You cannot use, for example, the age attribute as a key, because two students may have the same age value. For the same reason, you cannot use first name or last name, or even the combination of first name, last name as a key, because two different students may have same values on those attributes. So you cannot uniquely identify a student entity if you were to use that as a key for your entity set. But student ID has that property. Right? No two students can have the same student ID values, obviously. Yes?
Does the entire entity set have a key, like individually, or does each entity in it have their own key?
So the entire entity set has a key attribute, and each entity has a unique key value. Okay? So, do I answer your question?
Say it one more time.
Okay, let me repeat. Right? One entity set must have at least one key attribute for all entities. Each entity must have a distinct key value for that key attribute. Okay? And each attribute must have a domain which specifies the possible values it may take. For example, age is integer, name is string. These are what we call the domain of the attribute. As I promised you earlier, ER model is to be represented by a picture, right? So how do we represent entity as a picture? Okay. So the way you represent entities, by the way, the way you represent entity set, not entity, you never represent each single entity. You always represent entity set. The way you represent student entity set is by laying out a rectangular box with the name of the entity set in the center of that rectangular box. So for example, this is the employees entity set. And then each attribute is attached to that rectangular box using an oval box with the name of the attribute in the center of that oval box. And then finally, the key attribute is underlined. So for example, the employee entity set will be something like this, with 3 attributes, and SSN is a key attribute. What you can imagine is you will have multiple entities, employee entities, each representing a physical object, and each has different value instantiations to these 3 attributes. The only requirement is the SSN value must be different, but the name and log values can be different or the same for different employee entities. Does that make sense? So very simple, okay? So that's entity set. What about relationship and relationship set? Well, if you follow along the discussion so far, it should not be hard for you to figure out a relationship and relationship set. If you want to capture interactions between entities from different entity sets, from 2 or more entity sets, you need something other than entities, because these are not entities, right? For example, you have employees entity set, you have department entity set. What you want to do is you want to capture employee A works in department B, employee B works in department C, and so on and so forth. Right? How do you capture that? That obviously is not an entity set, because these are not entities. These are interactions between real-world objects. Again, that's something what we defined earlier, that's relationship. And the collection of the same type of relationships form a relationship set. Just as the collection of the same type of entities form an entity set. In the same manner, you're going to have relationship and relationship set. Does that make sense? So here is a relationship set. The way you represent relationship set in ER diagram is a diamond box with the name of the relationship set in the middle of that diamond box.
Does a relationship have to necessarily be between 2 entities from different sets, or can they be between 2 entities in the same set?
Excellent question, okay? Does relationship have to be for entity from 2 different entity sets, or can be for entities from the same entity set? Or I can actually generate your question a little bit. Does relationship set connect entities from one or two or more entity sets? Right? The answer is actually yes, it can connect entity from the same entity set, two entity sets, or three or even more entity sets. We will be discussing those later on. By default, we talk about what we call binary relationship set that connects entities from two different entity sets. So in this case, work seen is a relationship set. What you should imagine is the following. So what that picture actually represents is actually the following. So you can imagine you have a set of employees. This is the employee entity set. I'm going to use a dot, a single dot to represent a single employee entity. So what that entity set refers to is a collection of employee entities. Each dot represents an employee entity, and each dot has three values: SSN, name, and lot, where SSN has to be unique. Similarly, you're going to have departments. Again, I'm going to have a collection of dots, but these dots are different from these dots, right? These dots are department entities. Each also has three values: department ID, department name, and budget. The relationship set captures relationships between these entities. What is the relationship? Well, it's a line between an employee and a department. What does that mean? That means this employee works in the department. So if I denote this as A, B, C, D, E, F, and this as 1, 2, 3, 4, what this line means, employee B works in department 1. I can have, of course, multiple such lines. I can even have multiple lines for the same department. What that means is two employees working in the same department. I may or may not have this case, right? One employee working in multiple departments, depending on my business logic. That makes sense? The collection of these guys is what? Is your relationship set. Okay? Relationships can have attributes on their own as well. For example, for each of the line over there, I want to document since when an employee works in a particular department. That's something you cannot attach to either the employee entities nor the department entities. Rather, it should be an attribute specific to the interaction among them. That's why we may have attributes attached to a relationship set. What that means is each of those lines will have a specific value to it, which is the thing's attribute value. Right? Since when an employee works in a particular department. Which is right there over there. Okay, it's the same thing as I draw in the whiteboard over there. What time we have to stop? Is it 1:10? 1:10. That's the official time? Okay. All right. So we have 7 minutes. Okay. So that's the ER model basics. Actually, you know already, for the most part, you can claim you understand ER by now, right? Seems like very simple tools, but you can actually use these things, use this model to do really powerful designs, which I will illustrate in the next few slides. So going back to his question earlier, right, whether relationships that can connect entities from the same entity set, the answer is yes. Let's continue on this particular design. Not only in an organization you want to capture who works in what department, obviously you want to capture who manage whom, right? Who are manager, who are just employees, okay? So how do you capture that? This management relationship, if you think about it, are interactions among employee entities themselves. Right? Some employees are managers, they manage other employees. So these interactions are among the employee entities themselves, which means you're gonna have relationship set connecting entities from the employee entity set, like this. Okay? Some employees report to other employees who are managers. And you can annotate this design by specifying who reports to whom, right? Does that make sense? Picture-wise, what that means is you're gonna have, unfortunately, I do not have another color. You're gonna have things like this. Obviously, the collection of these relationships will be different from the collection of this relationship. That's another relationship set. Do you understand this, Gina? Okay. Next, I'm gonna introduce something that allow you to specify the earlier question I posed to you guys. Things like whether, for example, one employee can work for multiple departments, or can a department have multiple employees working in that department? How do we differentiate all these different designs? Does that make sense? Okay? So the way you do that is to use what we call one-to-many and many-to-many mappings. So, okay, I'm going to go directly to the example at the bottom, right here. By default, ER diagram assumes many-to-many mapping, which is this case. What I mean by many-to-many mapping? Many-to-many mapping means an entity from the left-hand side of a relationship set can participate in multiple relationships with the entities on the right-hand side entity set. Translate to our example, an employee can work for multiple departments. But it's many-to-many, right? So it's many on the other side too, which means entities on the right-hand side entity set can have multiple relationships with entities on the left-hand side entity set. Translate to our example, meaning a department may have multiple employees working in that department too. That's many-to-many. By default, when you draw only two lines connecting the entity sets to a relationship set, by default that's many-to-many. Unless you specify otherwise. What do I mean by that? Well, let's continue with the one-to-many example. For example, I have this requirement that an employee can work for multiple departments. Actually, but a department may have only one employee working in that department. That's that's not the example. Let's use the example I have in the slide over here. Let's say for each department, I'm gonna have at least one manager. I will select one employee to be the manager of that department. But this same employee can be manager of multiple departments. Do you follow me? So that's an interaction between employees and departments. However, this is a different relationship set from the work thing relationship set, even though they are connecting the same two entity sets, but that's actually a separate relationship set because it's a different types of relationships between those entities. So I'm going to introduce another relationship set on top between the same two entity sets and call that second relationship set managers. Okay? Does that make sense? Imagine I have another line. I draw a color. Let me illuminate this black color. Like this. Okay, I run out of colors, that's okay. Imagine I draw really hard here. So these black lines are different from this green line because they represent different relationships. They represent managed relationships. And for these managed relationships, imagine I want to enforce the following business logic, business rules. One person can be a manager for one or more departments, but the same department can only have one manager. Do you follow me? How do I capture that? What that means is this design here, so imagine I'm going to let me eliminate this green lines for working. I'm going to use green for management now. What that means is this is allowed. So I manage 2 departments. That's okay. But as long as you have a manager already, you cannot have another. This will be rejected because you cannot have that second manager for that same department. How do I capture this in my ER design? And this is what we call a one-to-many mapping. Why is it a one-to-many mapping? Because one employee can be manager of multiple departments. So one-to-many. But same department can only have one manager. So one on the employee side and many on the department side. The way you design a one-to-many mapping is to use an arrow coming out from the many side points to the relationship side. So this means this is many, this is one. So that's a one-to-many mapping. Translate to the diagram here. In other words, you cannot have another line connecting to this, and this dots because they already have one manager connected to them. I will stop right here and we continue. Oh, by the way, announcement. Unfortunately, I will be out of town for a workshop at NSF, for actually 2 meetings at NSF, really important meetings. So I will not be here on Wednesday, so we have to cancel the Wednesday class. I see you on Monday next week.
Moving down.